In today's tutorial we will have a look at the mechanistic details of the aldol addition reaction. We will choose as an example the aldol addition reaction of acetone with itself, this aldol addition product, while as we know rather easily there is the possibility to eliminate water, but then we have the aldol condensation reaction. So, aldol addition and aldol condensation work under basic conditions, but also under acidic reaction conditions. So, first let us have a look at the mechanism under basic reaction conditions. Well, we start with two acetone molecules, we deprotonate, then we will have such an enolate, and in close proximity that acetone. This enolate is a strong nucleophile, an ambident nucleophile, with nucleophilic centers at the oxygen and also at that carbon here. We have a rather large negative partial charge here. As a nucleophile it reacts with the more slightly positively polarized carbon here at this position. The electron density will migrate according to those arrows, and in equilibrium then this is formed, just protonating. Here we have deprotonated, here we can protonate again, then we are at the product of the aldol addition reaction. We have written it as free enolate, but usually it is better to draw it like this. There is generally a counter and countercation directly sitting at that oxygen. A metal center might be a lithium, a sodium, or a potassium. And if we draw it like this, then we can assume this metal center is a Lewis acid, will coordinate to the free electron pairs of that oxygen, thus activating the carbonyl activity of that, and just let the electron density migrate. Then we have here the metal coordinated alcoholate, and that metal coordinated to the free electron pairs of the carbonyl group, and just protonating then will also delivering here that aldol addition product. Let us change to acidic conditions. What is clear for the mechanism is the first step. In equilibrium, it is the carbonyl group is protonated. We will have this reactive intermediate, and then it can be deprotonated again, but at one of those two CH3 groups, and an enol is then formed in equilibrium. The equilibrium is by far on that side. However, this is regarded to be a reactive intermediate. And now the next step. This reactive intermediate, we can assume will react with the acetone, while we have a slight delta minus nucleophilic activity here at that carbon, again the slight delta plus as already here shown at the carbonyl group. If the electron density migrate, we could form such a zwitterionic intermediate mesomerically stabilized positive charge here the negative charge, and well, we can assume here we have an intramolecular hydrogen bridging bond, and that hydrogen will then hop over to that oxygen, and we have the neutral molecule. Well, but we can ask, is this an, well, convincing mechanism? Maybe this zwitterionic intermediate is a bit high in energy. There might be a better reaction pathway. Maybe simultaneously that hydrogen migrates to the oxygen and the carbon-carbon bond is formed. Well, such a mechanism would look like this. We would run through a transition state like that, and then directly forming this molecule. This mechanism reminds us of the so-called ene reaction, which is closely related, for instance, to the Diels-Alder reaction. Maybe you will have a look for comparing this type of mechanism to the ene reaction and the Diels-Alder reaction. But as I said, the reaction works very well if we have a large partial negative charge here, and then we have a strong nucleophile. Maybe it works also very good the other way around, having an increased reactivity here, and we can at that carbonyl carbon, we can achieve that just by protonating the carbonyl group. Well, we have this already here in that mechanism of the equilibrium formation. So a strong electrophile with a moderate or comparable weak nucleophile, it will also react rather fast, giving this intermediate, and then we just have to deprotonate here and are at the stage of the aldol addition reaction. So I would say this is the most convincing mechanism for the reaction under acidic conditions. Let's mark this. And on the other hand, under basic reaction condition, this should be regarded as the most convincing mechanism. Thanks for listening.